Hello everyone, here is another video for IB Physics Review for First Assessment 2025. This next series of video will be focusing on reviewing the physics data booklet for Physics IB. This is aimed at higher level, which means I'll go over every single formula in this formula book over multiple videos. Alright, and make sure that you are if you're studying, watch the following videos and also combine it with the review. Okay, combine it with the review to be thoroughly prepared for your IB exam. I will also do a brief review of each unit, okay, as we go through the formula. Okay, as we go through the formula, so that way it will serve both as a review, mini review, okay, as well as a formula sheet annotation. So without further ado, let's get started here. All right. We'll start by looking at the fact that this is a very thick formula book. Okay, has 13 pages. All right. So the table of content is helpful. Okay, helpful of course, but the best thing is make sure you are familiar with where your unit, where each concept is in which unit, and have a rough idea where they are during IB exam. Okay, if you have to look at the contents page each time, it might slow you down a little bit. So once again, I highly recommend that you actually know where everything is. Okay, so I will do a quick overview. Okay, when you flip it through, if you have a copy provided to you by your teacher, you should have it handy with you throughout, and you can annotate it on your IB formula sheet that you have, or at least you can flip it around, look at it, and so just get familiar with it. Either way, I highly recommend you have a physical copy, if you have one, with you through this process. All right, start with the math equations. These are pretty easy. Okay, and then uncertainties and constants, and then you have the metric prefix. This will help you for unit conversion. All right, and then some other unit conversion factors. Then you have the circuit symbols. The new curriculum have not explicitly stated you need to draw them, but you need to be able to read them. So these will become really helpful as well. And you have the EMR wavelength, okay, correspondence, okay, right here as well. All right, and then you have chapter A, B, C, D, E in order. So that's it. All right, so that's your order. So basically all the physical constants are in the front. The unit conversions are right after that, and then the circuit symbols, and then the formulas. Okay, so you have a rough idea where to find them. Okay, where to find them. All right. So I will do the review for the front one pretty quickly because that's not the main focus. These are math skills you probably already have before you even started taking physics. So these are the mathematical equations. So for area, volume, stuff like that, okay, you expect to know. The only one on here that's not, the only one not on here, I mean, that you should know is the area of a sphere. And let's hope you know. Let me grab the pen to annotate. Area of a sphere is area is equal to, for some reason this pen cannot draw horizontal lines very well. Okay, let me zoom in. PDF doesn't like horizontal lines apparently. There we go. 4 pi r squared. Why strange is not on a form. Well, you don't need to, you probably know it already. But why strange is not on IB formula sheet, despite the fact that formula is used more than the actual volume, like way more, which are strange. But I guess it's in their formula when they used. All right. Vector addition. I guess this is the only thing that's sort of physics. It's how you draw vector addition. Okay. I usually don't draw it this way. I usually don't draw it this way. I usually add them tip to tail. It's a very poorly drawn one. And then that's a vertical, that's a horizontal, and then you do trigonometry on using that, okay? Because you will need to use trigonometry anyway. So instead of just telling you what this is equal to, you can actually see the trigonometry relationships. Okay, of course they're perpendicular to each other. Yeah, apparently if I, what about now? Quick interesting problem. How much do I have to zoom in so I can draw horizontal lines uninterrupted? Alright, cool. Yeah. Alright. So that's the math formulas, and then you have uncertainty, which in the previous video I have went over, okay, briefly, but here they are. They're on the formula sheet. These are the ones you're expected to know. Okay, the other ones they'll either provide to you in a question, okay, or you will not be tested on at all. And you have the fundamental constants. Okay, fundamental constants. They're pretty self-explanatory. You will see them in the formula sheet, in the formula sheet. Oh, something fell. You just need to know where to find them. Okay, some of these are actually not used in the formula at all. It's just a complete formula. It's just a complete variables that's all used commonly in physics. Okay, even though they may not be referenced explicitly in the formula, they may be indirectly referenced in the question because they're actually hidden in the formula. Okay, for example, well, this one are not hidden because you have both versions. Gas constant and Boltzmann's constant are actually very, very closely linked. For instance, right? Same thing as Coulomb's constant and the permittivity of free space. So they are linked together, but yeah. So maybe they're not explicitly stated, but the question may hint at it. Metric multipliers, pretty straightforward, speaks for itself. And then unit conversions. Once again, something you probably know mostly, but if not, you forgot what a kilowatt hour is, you forgot what AU is, they're all here. All right, circuit symbols, already went over that earlier, and spectrum light. All right, so that's the what we consider the first portion of the data booklet, the data part. Now we start with the formulas. Okay, this video will focus on going with the formula and a quick review of the formulas in Unit A. Unit A, which is called, quite cool, space, time, and motion, but it's just called, I just call it, because that's what it is, mechanics. Alright, cannot draw horizontal lines until zoom in. Mechanics, okay? This is the foundation of physics. Mechanics and relativity. That one is not. Relativistic mechanics, I guess. Come on. Oh, I think it's trying to guess what I'm writing. Alright. Alright, smaller, I think you'll be okay. Alright, bigger. Or zoom in bigger. Alright. So, once again, I'm assuming the viewers are mostly students following the Alberta curriculum, even with the EPSB. So these formulas should be very familiar to you, even though they look different. Okay, these are what we call the kinematics equations. Okay, there actually is 5 of them in the modified version, but I think I should annotate them correspondingly. All right, so S really won't let me write. There we go. S is displacement. This is not letting me write as well as I thought. Which in non-IB or Alberta curriculum, they use D with the arrow on top. All right. Now, not to mix up, it's actually kind of important, is that U is actually initial. Have to write big gestures. Velocity. So VI in the old non-IB notation. V is the final velocity. Okay, do not mix it up. Okay, and then A is A and T is T. Acceleration. T is time. I'm not gonna write it. You know what? I might as well. Time. All right. Because the letter used in IB, okay, usually these are also called the Suvat equations. I'll write over here. Suvat. If you hear Suvat, that's what we're talking about. Okay, that's what we're talking about. All right. There's not too much to review here because the formula is pretty straightforward. But I do want to mention questions that could be asked. In fact, very popular. Okay, are things. Well, not only do you need to know where the formulas come from. Okay, things like I have my notes here. No definition of what they are. Know how the formula is derived. No difference between uniform motion and accelerated motion. So behavior. Oh no, that was something different. Okay. So, position, how to describe? Yeah, uniform, non-uniform. So you have to know uniform. Be careful. I know in my class I like to use PP0, PP1 because that's what the Alberta formula sheet indicates. The physics principle associated with this. Okay, but that's only for Alberta curriculum. It's not for IB. So do not use those physics principle 0, physics principle 1, or whatever. They don't know what they're talking about. Okay. So make sure you know the difference between uniform and non-uniform motion. Newton's laws is the next one, but it's related to Newton's laws. Now the pen is acting up again. See what's going on. Undo those last few. Uniform. Any more? Motion. All right, and of course, the most interesting one is the concept of projectile motion, two-dimensional projectile motion I'm talking about. Projectile motion, all right. Maybe I'll type this. Actually, let me see if I can type. There we go. Oh, there we go. It won't let me. Oh, created one over there. When can I create one over like here? Testing as I go. My tool was working well when I was warming up, but okay. I'll just write. I'll just keep writing it. All right. And you should also know the effect of like resistance and friction, specifically air resistance. Okay, but in any fluid, so you need to know the effect. Okay, effect. Of air resistance. No, missed. Okay. Now, of course, that just for this unit, it quickly gets more interesting when I move into the next part, which has way more formula. Okay, momentum and forces. Okay, momentum and forces. You'll notice something about circular motion at the end as well. Okay, so I'll go over each in detail. These two are about friction. Okay, first one is when it's static and unmoving. So this one is, I guess there's not too much to say. I'll write over here. Will it fit? Okay, won't fit. I'll write it over here. All right, so here it's static friction. Here friction, it's static. Static friction. here static friction. Okay, so mu s, of course, is the coefficient of static friction. Is the coefficient of static friction. And the second one, of course, is the kinetic friction, or sometimes called the dynamic friction or sliding friction. D here stands for dynamic. I'm going to call it dynamic and kinetic. Dynamic or kinetic, sometimes also called sliding friction or sliding, because when rotating it's actually static friction. Okay, because as we learned, when rotation was not slipping, the motion is relative velocity is actually 0, otherwise it's slipping. Okay, sliding friction, I'll just add F like that. So mu F is the coefficient of static friction, right? Mu D is the coefficient of dynamic friction. All right, that's the frictions. All right, it's important to note, I'll write a slide over here for review. If you have a friction is always opposite motion, so you can say it's almost always negative. Okay, these are vectors. Okay, oh, I guess I should also mention these are vectors. These four are vectors. So you have to be careful with direction. You may have to use the vector addition to figure out how they work. Okay, all forces are vectors. Forces, there are both forces and momentum are vectors. The formula will only give you the magnitude. You have to determine the direction otherwise. Okay, there are vectors. You have to find direction by context. Which means FBD. Okay, draw FBDs. Okay, not often you're not required to draw FBD for your IB exam, but it's still a good idea to do so. My handwriting is bad because somehow the pen is not working as well as I thought. All right, let me zoom in. All right, so for friction is opposite the motion, okay, at least for dynamic. So this one is always opposite the intended applied force. Opposite the applied force. Whatever force trying to move it, static friction will oppose it. Okay, oppose it. While kinetic friction will always oppose the velocity. Okay, velocity. All right. So there's that. Okay, I'm gonna try to type again, but always bring to the top. All right. I'm a little sad because it's not working. No, it's typing the for text. Let me try this one. I'll try to type this one. The next one is elastic force and Hooke's law. All right, Hooke's law. Well, it's Hooke's law applies specifically to the applies specifically to spring. Okay, so here H of course is the H of course is the FH is the force, spring force. Okay, sometimes called elastic force from the spring. Okay, and K is what we call spring constant. All right, and then X is displacement from equilibrium, rest. Let's say from rest position. All right. Oh, seems to be working pretty well actually. Maybe I'll just keep doing this. All right. So displacement from rest, and this is basically how much you stretch or compress the spring. Stretch or compression. Okay, how much you stretch or compression of the spring. That's basically what it is. That's what it means displacement from rest. It's not a absolute displacement, okay, but specifically from rest position. All right, just be careful. This one I will probably have. Let me have to draw a little bit here because I do have to highlight. No, I cannot highlight this one. I'll draw then. All right. The negative here is indication of direction. So both of these are already vectors. All right. This is indication direction. Okay. The direction is always opposite. Okay. The displacement is always opposite that of the force. Okay, the force and displacement are always in opposite directions. Okay, always in opposite directions. The next one. Okay. Now let me put it where I want. That's good. It wasn't working earlier, and when I was setting it up, it's good though. All right. Next one is known as Stokes' law. Okay, next one is known as Stokes' law. At least a version of Stokes' law. Specifically for spheres. All right. This is talking about the drag force of a sphere in air. All right. Now, for other objects, it's not a sphere. The formula changes a little bit because it does depend on the drag coefficient. Okay, drag coefficient. However, for a sphere, it's perfectly fine. We can use this formula. Specifically, F D is the drag force. I guess I cannot write the symbol, okay, for eta, but that's eta. So I'll write eta. Okay, that's the symbol. That's the viscosity of the fluid. All right. So I will just write eta right beside it. That's what eta is. Eta. All right, going back. All right, and then of course R is the radius of the sphere, and V is the speed of the sphere. Notice I said speed, not velocity. It's because direction does matter here. Velocity, the direction does matter here. In the sense that, the velocity will always, the force will always opposite the direction of velocity. So if anything, if we have to put direction into the formula, it would actually be negative. Like that. Actually be a negative. Like that. So it should be negative that because the force always opposite velocity. So basically it behaves like friction with a different formula. Okay? The most interesting thing relating to the drag formula okay, is the concept of terminal velocity. Your terminal velocity, okay, which is 1 FD. This one I have to write. It's equal to gravity. So you won't fall any faster. With self-accelerating, when direct force is equal to gravity, that's when velocity is terminal velocity is reached. Okay, so velocity when this happens is called terminal velocity. All right. So that is Stokes' law. All right. And then the next formula is called buoyancy. Okay, a lot of type, so I'll type this one. This one is buoyancy. FB is buoyancy. Or buoyant force, but buoyancy is just easier. Okay, buoyant force, buoyancy. Okay, this one you may know already, as this is the Archimedes principle. Okay, it's not usually named. Okay, basically this is just the force of gravity. Okay, of the displaced fluid is equal to Fg of displaced fluid. All right. One object is moving in a fluid, both drag and buoyancy affected. Okay, so it's important. Rho here, or P, people call it P, is density. V is the volume of the object. Basically the same as, let me move this a little bit out of the way. Displaced fluid. More. I'll put down here. Object of a displaced fluid. All right. And G is 9.81. So that's a constant, so I'm not going to highlight this one. All right. The key thing here is, I will still write the rho in. The key thing here is that this is just the gravity of the displaced fluid. Okay, the volume of the object, of course, is gonna be how much it displaces. Okay, one object. Let's say you have some liquid. Then you have a small ball falling. This ball experiences both Fg. Of course, it's on Earth. FB, not both. Well, three things, I guess. It wouldn't be both. Erase that. Not both. All right. But experience Fg, Fd, and Fb. All right, and they together create the effect of an object slowing. For air, it's not much of an issue because the buoyancy of air is very small. So we usually ignore the effect of buoyancy for air. It's so small because density of air is so small. So in air, this is not a concern. But in liquids, okay, especially like water, this may become important. Okay, may become important depending on the question. Okay, depending on the question. All right. Continuing on to the next formula. Now, next formula is gravity. Everybody knows this one. So popular, but I'll properly write it down. So M is mass. G is G. Gravitational field strength, I should probably say. It's off the screen, but I did type it right here. All right. Fg is probably pretty common. Okay, so yeah. Something not on here are forces. Okay, like electric forces and magnetic forces, which formula will be seen later, but they behave like these forces. So even though those forces are not on this page in our future unit, okay, their behavior is exactly the same. So you are actually expected to combine other forces with these forces. All right. So make sure when you're studying, you're not just thinking too like limited and saying, oh, this must be unit B, this must be unit D. No, all the units actually start crossing over. So FE and FE and FM are just the same. So I got type it in, write it in. Don't forget, FE and MM are also used in this unit questions as well, if appropriate. So FE and FM. Okay, apparently that's how I have to write to make it work. So there we go. Now, forces obviously follows immediately by the concept of Newton's laws, okay, which is formulated using this way. Okay, using this way. First is momentum. Okay, momentum. Momentum is once again one of those things that are very well known. So I don't need to spend too much talking about it. Okay, but momentum is basically how Newton formulated his three laws. So just know, you not only do you need to know Newton's laws, that's uniform motion, accelerated motion, and reaction motion. Okay, you actually do need to understand how it's formulated in terms of Newton's laws. But in order to do that, which I will review, I need to talk about the next formula as well. Next one, you see this J here. If you're in Alberta curriculum, you probably haven't seen it, but J is actually impulse. And it's very important. Impulse is actually the change in momentum. That's not written down here. Okay, that's not written down here. Okay, in the Alberta curriculum, we usually write it as delta P, so it's obvious what it means. Yeah. Okay, but in IB, it's actually J. That's what actually engineering physics uses quite a bit in most university. In most physics classes I've taken, we don't use J. I mean, some teachers may use J, but most of us don't like, because it's this change of momentum. So it's changing momentum, so it's actually very, very important. Given it's not on a formula sheet, given that momentum, we usually deal with things where mass does not change usually. So usually you may think of it as F delta T. This is formula on the Alberta formula sheet, nonetheless. Okay, so that should go a little bit deeper. Okay, M delta V. But this formula is not on the IB formula sheet, so you're not allowed to just like use it, but you do have to mention impulse in some form. Okay, so make sure you know impulse is changing momentum. So now I'm allowed to actually state what Newton's law is. Okay, which is, well, the first one is, okay, first law is, type it in. First law is impulse is 0 unless there's external force. Without external forces. All right. Unbalanced. Well, I should say with balanced external forces. That makes it more appropriate. All right. Second law. J is not 0 with unbalanced forces. Specifically, the force, the net force, I need to add the net in here, otherwise it's not quite correct. The net force, okay, the net force is equal to change in momentum, aka impulse, over time. That's where this formula comes from, actually. That's where this formula comes from. And if you rearrange it, if mass stay the same, then you can get that turns into MA. This is a more famous formula, but Newton actually framed it in terms of impulse. Okay, impulse. And for those who like calculus, it's actually a derivative of impulse over time, because Newton invented calculus for this. So momentum, okay, changing momentum over time. And the last one, the most easily gotten wrong one, is basically a force requires two objects. a force must act on two objects at a time. So every force acts on two objects at the same time in opposite directions. Which means you have two things hit each other, right? One force, two objects hit each other. That means J1 equal to negative J2. That's what it says. Okay, so for each collision, okay, the impulse on one, because no matter what forces are there, all the forces from the first object must also act on the second object in the opposite direction. So the impulse on them are exactly opposite of each other as well, and the same amount. Same amount, but in the opposite direction. Alright? That's impulse. Okay, and momentum, physics 30. So, and of course IB. Last is my personal, I must say, favorite. Okay, oh, scroll too far. Go back. Alright, our circular motion. Let me type it out. Last bunch here, circular motion. So A is centripetal acceleration here. Centripetal acceleration. V here is, be careful, it's not the speed. I mean, it is the speed, but it's tangential velocity. It's considered linear, but it's moving in a circle. Alright, R, of course, is radius. Alright, the omega here, the W looking thing, okay, because everybody likes to call it W, so I'm going to call it W here, but it's actually omega. It's what we call angular velocity, or angular speed. We shouldn't use velocity here because they're all magnitude. Maybe I should change all this all to speed. It's more appropriate. Change that. Oh, that took a little longer than I thought. Angular speed. And T is period. Alright, so that's what these formulas stand for. And circular motion have its own challenges, and there's quite a few things covered, so I will not able to go over in great detail. But the key thing here is, we'll see a little bit later, is that angular speed and linear speed are closely related to each other, and you should be able to convert between one or the other. Right. Alright. Turns out it's taking a lot longer than I thought, so I am going to speed up a little bit, okay, as we talking about A3, okay. I will not go into as much detail as review, but mainly focus on what the formula is actually talking about. First one, okay, the first one is work. Okay, first one is work. Okay, W is work. F is a force doing that work. S here is displacement. Alright, and zeta here, the angle, is between the force and displacement direction. So I didn't address this one. So basically, if you have a object, what? I can't draw it over here. Okay, I'll draw it over on the left. All right, if the object is moving this way, oh, we're just writing D, S, and the force is this way, then that angle here is zeta. That angle there is zeta. All right. The second formulas should be very familiar. Okay. They are, of course, the kinetic and potential energy. So first one is kinetic energy. Okay. That's what EK is. This formula is very popular. Okay. Very popular. So I'll not explain too much detail what it is. All right. Just know that you know MV what it means. But just know that P here actually means momentum. So you can actually convert directly from momentum to kinetic energy, okay, with this formula provided to you right here. All right. You are actually expected to know how to derive from one to the other one. I will not show it here, but you can actually show these two formulas for kinetic energy are actually the same. The next one should also look quite familiar. This one is gravitational potential energy, but specifically this is change in gravitational potential energy. And that's because, if you remember from class, okay, gravitational potential energy actually require a reference height. You cannot just say how much potential energy you have. You have to choose reference height. Once you choose reference height, then you can write EP equal to mgh, where h is a distance from the reference height. But technically, we do not quite have that. We only have a change in reference. Change in potential energy for gravitational. All right, just make sure you know that small detail, important, actually quite important conceptually detail. The next one is what we call the spring energy, okay, or elastic energy. All right, and of course, that's EH. Of course, in this case, K is spring constant. And delta x is displacement. However, this is displacement from equilibrium. Okay, once again, this delta x here is how much it has moved from where it normally is, right? So you have to actually account for the fact it's a change in position that gives this energy. Both of these are potential energy. Okay, kinetic energy is kinetic energy. So both of these are potential energy. Okay, what's the potential energy? Okay, and potential energy actually only works for conservative forces. Okay, non-conservative forces cannot have potential energy. They only have, well, kinetic energy by taking away actually kinetic energy. All right, converting some other forms of kinetic energy, but I digress. But know that these two are potential energy because these two forces are conservative. There we go. All right. Next is power. Okay, I feel like a little bit Emperor Palpatine here. Unlimited power, but it won't let me write here. Okay, right here. Power. All right. Power is change energy over time. Okay. Power will show up multiple times, but that's always what power is. So in future units, power always actually mean this. You can actually show that it's equal to FV if F is constant, right? It's equal to FV. So F here is the force, and V here is speed. Okay, once again, it's very easy to show that just by using work equal to force times displacement. Okay, just note it's supposed to actually, if you want to be accurate, you actually should have a cos zeta here. Just like, oh, it's going too far, just like work here. Okay, so if you want to be appropriate, that cos theta should be there for you to be completely correct. However, usually ignored because we assume the force is doing work in the direction of displacement. All right, and last but not least, okay, last but not least, in A2 is a concept of efficiency. Efficiency is usually represented as a percentage. Okay, usually as a percentage. Okay, won't let me write S anymore. There we go. Usually a percent. All right, so this is, of course, efficiency. Okay, you'll see efficiency again later. Okay, but that's what it actually means. All right, that's A3. Continue on forward. Now on to A4. A4 gets a little complicated. A4 is a true IB unit. Okay, that's talking about rotational dynamics. Okay, since move. Okay, but you'll see all the formulas are actually analogous. Okay, analogous to that of the kinematics dynamics unit, because they're actually very similar. So as I explain what they are, it should become pretty clear what they are. First is analogous of what we consider force. Since there's quite a bit to talk about, I'll write that word on this side. First one is it's a rotational force. The force actually causes something to rotate. It's called torque. Okay, that's what tau is. All right, of course, F is a force causing a torque, causing rotation. R is a radius, and theta, the angle, is the angle between, the angle between the force and the radius. Okay, so direction of the force between the force F, I'll say F and R. So what I mean, let's say, okay, I'm gonna draw a picture here. So let's say there's a arm rotating over here. Let's say here's a central pivot, and you have an arm rotating, right? A stick rotating around this pivot. Then the force pushing on it is that, and the angle. So this is the arm, R, and this is the force, F. And that angle there, theta, is the angle we're talking about. It's not working. Longer. There we go. That angle there is theta. So between the force and the radii. All right. The next is what I call, angular or rotational kinematics formulas. All right. So these are all come as a group. Okay, these all come as a group. I'm gonna do this actually. Does come as a group. These are what I call rotational kinematics. All right. So, I realize all these symbols are weird, so I cannot really use the type. I'll type it out. I'll just type it out here. I'll write it out. I mean. So theta is in radians. Delta theta. What? Is angular displacement. This is called angular displacement. It's measured in radians. Must measure in radians, otherwise it won't work. All right. Omega is angular velocity, initial and final. I will not write the whole thing out. I and F speaks for itself. So it's angular velocity. Which is actually just change in theta over time. Just like displacement over time, right? Displacement over time. All right. This is okay. I guess this is just like uniform, just like kinematics. This is not exactly true. Okay, this is only for uniform. Okay, angular motion. So, but the idea is it's changing that. Once again, for those who know calculus, it's a derivative of angular over time. So, but this is not entirely correct. So I put the quotation marks. You know what? So annotating and review, I should actually erase it because that's the intuition, but that's not what it actually is. So I'm gonna erase it. Oh, then erase as well as I thought. There we go. All right. Now, what is important though, what is true though, is that angular velocity can be derived. Okay, this one can be shown to be equal to 2 pi over t in a future unit actually. What's going on? T, which is equal to v divided by r. So tangential velocity here divided by r. So this is good to know. Yes, it is on a later formula, but I think it's a good idea to show it here where everything else is. All right. Alpha is what we call angular acceleration. I'll write that. And time is time. I'm not writing t. Okay, time is time. All right. Now, everything here I've written here are vectors. Okay, they are vectors. The direction associated with them. The direction associated with them are either clockwise, counterclockwise for IB. It actually does get a little bit complicated. Oh, what's going on? They're complicated when you actually talk about three-dimensional vectors because they actually point in and out of the page. But that's not something you need to worry about right now. So it's either clockwise, counterclockwise, and its formula are actually fairly easy to remember because they're just their linear counterparts from 8.1. Linear counterparts from 8.1. All right. So these are basically kinematics, how you describe those. There's no projectile motion, however. You just have to know how something moves. Now, in order to talk about actual dynamics, things start moving. When you talk about mass, however, only the mass that is being rotated, okay? Because mass resists any kind of movement, but they resist motion. Okay, they resist rotation more than they resist linear motion. Okay, it's harder for them to move the further you are from the center. So the formula for mass, or what we call moment of inertia, is actually proportional, of course, to mass, as you can see, but also to radius squared. Okay, which means further you are from the center, the harder it is for you to rotate. Okay, All right. And of course, this is treating every single mass as point mass, but a rotating body is rarely a point mass. It's going to be a disk or something, so you have to actually add up all the moment of inertia. Now, this only works if you have multiple point masses. If you have a real disk that's continuous, you have to use something called integration from calculus. You don't have to worry about that for IB. They will give you the moment of inertia for specific general shapes. Not for multiple point mass. You have two balls, for instance. We expect you to add it up. Okay, but if you have a disk or a sphere or like a ring or whatever, it's usually provided to you. So write it down. For non-point masses, formula given. Just like in real practice, because nobody actually memorized the moment of inertia for a sphere or a ring or something. You can calculate it. It's not like too difficult. It's a little lengthy, but you don't have to memorize it. Okay, you don't have to memorize it. So with mass and acceleration, we naturally get the formula for torque. This is just Newton's second law. Newton's second law for torque. So I don't need to say it. Net torque. Oops. I guess I'll say net torque. I'll just add that small disclaimer on there, which is it should be a net, just like I did earlier for net force. Net. So you imagine you have multiple forces, right? You have multiple forces, right? This force pushing this over here, this force pushing over here, this force pushing over here, right? Both bunch of forces pushing. Some force may pushing this way, right? Bunch of forces. The resulting torque by all the forces is equal to that. Okay, force equal to that. A very major concept tested using these, okay, is the concept of rotational equilibrium. So basically, you have an object, maybe not rotating at all, hanging in static because there's a string or something. There's a force holding it. Let's say it's a wall here. The string holding it in place. There's some weight holding it down. Some kind of weight holding it down, and you have to calculate. Okay, how much force does the hinge over here experience, right? Or how heavy is this weight, right? Or how strong is the tension force? Okay, so you'd be using that the sum of all forces are 0 is 0, but sum of all torques is also 0. Okay, if you use that, you can actually solve for the system and understand which the strengths of each force. So that's what's usually associated with this. Basically, kinematics dynamics of rotational motion. Okay, rotational motion. All right, and then next we're moving on. Next is something that's quite popular. And next one is called the angular momentum. Okay, as you can see, it's mass times speed. So this one is just angular momentum. And it's very important to note that angular momentum, okay, just like regular momentum, it's always conserved. So make think about the conservation of angular momentum. Right, angular momentum. Now, notice that mass is momentum is for point mass at least. Point mass. Okay, for a point mass, I is just mr squared. So, and omega is v over r, as we saw. This one is also equal to, you know what, I'll type it. I shouldn't have to type it because it's not letting me draw. L is also equal to mvr. Well, we've seen this, okay, in a future unit called Bohr's postulate. Because Bohr did this exact same thing, okay, did the exact same thing for that. All right. The rest should be pretty similar in that this is just angular impulse and changing angular momentum, angular impulse. Both versions, force times time or change in momentum. So these are both angular impulse. Angular impulse. Nothing much to say here. It's angular momentum except changing. And last one is rotational kinetic energy. Okay, rotational kinetic energy. The formula is very similar to the kinematics linear counterpart, so I'm not explaining too much these here because the most important thing I want to explain are basically already explained for the linear counterpart for unit for A1 through 3. All right, 1 through 3. The only thing I try to connect are the special things for rotational frame. All right, rotational frame. All right, last but not least for this video, we're going to talk about, okay, we're talking about 8.5. Okay, 8.5 is Galilean relativity. Galilean relativity. All right, so all of these actually, for both Galilean especially, they all use the same variables. Okay, I just want to clarify that these are classical relativity, Galilean, and these are special relativity. These are special relativity. All right, and I'll just list what everything means here. Okay, I'll zoom zoom out a little bit. All right. I will not be able to drive a lot of things here, so there's gonna be quite a bit of. This is just how it works. All right. So first, x prime is position of a event. Okay, you know what? Let's put it this way. Two reference frames. There is a inertial. There's an original reference frame. Okay, that's not primed. And then there is a moving inertial reference frame relative to that original one. There's moving, still inertial though, constant speed, frame relative to original. That one is marked with a prime. Okay, so I'm going to call this A and B. I'll do some examples so you know what I mean. Okay, and B. So x prime will be the position in B, measured in B. B, and x will be position measured in A. And V, okay, V is the relative velocity, not speed, velocity of B to A. So how fast B is moving relative to A. Right? How fast B is moving relative to A. All right. So I don't have I write the rest if you want. So T prime is a time in B. T is time in A. Okay. U is speed. Oh, U prime first. U prime is speed measured in B. U is speed in A. There we go. So that's everything. All right. The Lorentz factor is gamma. Okay. It looks like R. It's a Lorentz factor. Okay. That only exists in special relativity. Lorentz factor. Okay. And c speed of light. I'm writing it down. All right. So this applies to basically everything here. Okay, everything here. All right. The next little bit are what we call basically the space-time diagrams. Okay, space-time diagrams. Okay, I'll type each of them out. All right. This is the distance in the space-time. So this is what we call space-time interval. Basically, it's distance in a space-time in space-time. Distance in space-time. So notice it's basically Pythagorean theorem, except it's subtraction because it's not a Cartesian space. Okay, subtraction. All right, so you can remember hard way, but basically it's Pythagorean theorem, except weird. Let's call it that. Pythag except weird. Okay, that's where it comes from. Okay, it's time minus space. Time squared minus space squared. Okay, what you need to remember. The next are what we call Lorentz transformations. Okay, so not transformations. Time dilation and length contraction. Stop. There we go. This is time dilation and these are time dilation and length contraction. So let's write it down. Here is time dilation. And next one is length contraction. Basically, if you measure time in one frame and you measure time in a different frame, this is how it changes. Delta zero is what we call proper time and proper length, which is when the object at rest with the event measures it. So basically something, if the event is to measure itself, that's what it gets. So these are called proper. So T0 is called proper time. 0 is called proper time. Once again, proper time just means, the time, time measured by itself. If an event is measured by itself, what time will it take? Well, here, L0 is proper length. Proper length is what, once again, if the object is to measure itself, how long will it be? Okay, how long will it be? So that is proper time and proper length. Last one is exclusive to the space-time diagram. It's not just using the property of space-time diagram itself. Okay, let me save this quickly here. Just saving it quickly here. Let's see, IP review. Yes, saving it quickly. See all my stuff publicly. I'll take some time. And last one is basically if you have a space-time diagram. Alright, then you can find the angle. You can find the speed using the angle. So this one I'm going to have to draw out a little bit. So if you have space, time diagram. So if you have space here, CT here, okay, then the slope of the line is equal to C over V. But the slope is just 1 over tangent. But if you measure the angle here, the slope is just 1 over tangent of the angle, right? But this is 1 over tan theta. So you can get the speed using this formula. So I'll type it out. Speed from a space-time diagram. Okay. But the key thing is it's measuring slope. So that's why I did this picture first. All right. And that took longer than I thought, but that is chapter A. All the formulas chapter A. Thanks.